What's up, coders? Welcome back to another episode of Conquering the JavaScript Interview with this little mini-series of Sorting Algorithms Unleashed. Today we're going to be inserting ourselves into the world of the insertion sort. You can probably tell from the title of the video and the thumbnail as well. This classic algorithm will let us sort out our problems by inserting them into their rightful place. I promise it's a less sorted affair than it sounds, so buckle up and let's start diving into this fascinating algorithm together. So we're going to continue our algorithm series here on sorting algorithms. That's redundant, on sorts. And we've talked about bubble and selection up until this point, and logically I'm going to do another simple one here, which is the insertion sort. Just like I mentioned in the previous videos, I will be highly surprised if you're actually asked to code this one in an interview. Again, get in the comments down below if you were asked, so I know that if it's more commonplace than I personally think, then in that case, I'll tell y'all to memorize this code a bit better. But remember, the bigger picture to take away here is understanding how these algorithms work, being able to describe some of their pros and cons and compare them against against each other, which will be what you're going to be more likely to do in an interview as a beginner anyway, right? So, the insertion sort maintains two parts or two regions of an array. It has a sorted and unsorted region, which will make sense when we write the code out and visualize what we're doing here. And we're going to start thinking with the insertion sort that the first element is already sorted, right? So then all we have to do is go to the next element in the region and compare which one is, again, a taller or shorter book. In our bookshelf analogy we've been using for all these sorts. And basically, over time, it will have a region where it sorts the sorts as it goes along. So there's like a whole bunch of potentially unsorted items and then a region of sorted stuff it's working on as we move along, right? That's where the name insertion sort comes from. It takes the next element from the unsorted region and then inserts it in the correct position in the current sorted region, right? So that's where insert comes as a name. So like our bookshelf and librarian analogy we've been using in the other videos, I'll start with this one here. Imagine we're a librarian. We got a bookshelf with books of varying heights, all jumbled and unsorted. And we want to arrange them in ascending order in their heights, just like we always have been. I mean, these are the sorting algorithms. It's the same premise for all of them. But using the insertion sort method, here's how we're going to approach this problem. We're going to start on the left end of the bookshelf, right? Or the array. Remember, the bookshelf is the array, and the books are the elements of the array. The first book, we're just going to automatically consider to be sorted. It's the only book we've looked at so far. We're going to look at index 0 and go, this is already sorted. So from there, we're going to go to the second book and check to see if it's taller or shorter than the first book. If it's taller, it remains in place. If it's shorter, we insert it before the first book. And at that point, the first two books on the shelf are sorted against each other. That's where the sorted region is, and every other book we haven't looked at yet is the unsorted region. So then we're going to go to the third book in the unsorted region. If it's taller than the second book, it remains in place. If it's shorter, we shift it to the left as many times as needed until it's in the correct position. It could be before the first book or before the second, or it stays at the third, right? So basically, you get the next book from the unsorted region and then sort it or insert it into the correct place in our sorted region. And again, that's where the name comes from. So we continue that process, always looking at the next unsorted book and inserting it into its correct position within that sorted region. And after each step, after completing all that stuff, we should be left with a bookshelf in a neatly sorted ascending order. And just like the rest of these, the code on this one isn't particularly hard. So let's go ahead and look at our prompt here for insertion sort. Implement an insertion sort algorithm. Same input and output we've been expecting through this little mini series I'm doing here. So let's continue on. Right, so with that analogy in mind, let's actually write out some code. We got our handy dandy function ready to go with our input array ready to test. So just like in our analogy, we are going to be picking up not the very first book, index 0, because we're going to consider that book automatically or already to be sorted in our assumption here. Then from there, we're going to look at the second book, aka index position 1, and then just moving on and potentially doing a number of comparisons every single time we grab a new unsorted book into our sorted region. So this is going to represent looping through our list of books and our sorted region, which once again, the for loop is going to be our tool here. We know exactly how many times we're going to have to traverse over this array, which is each unsorted element we're looking at here. But again, we don't start at index 0, we start at index 1 because we're making the assumption that index 0 just is the first unsorted book or first sorted book we have. So we're going to go ahead and start at index 1 in this case rather than 0. We are going to continue till surprise. We get to the end of the array. We're going to increment our iterator I by 1 time. For some handy dandy variables, I will go ahead and do the following. I'll go ahead and get a current variable just for readability, so we have to write RI over and over and over again if we can help it. And this is where we're going to deviate a little bit from our other sorting algorithms, where we typically had yet another for loop nested inside of here. We're actually going to be using a while loop. So I need to have some kind of iterating variable created for my while loop. We'll do it out here, which we'll be going to compare, in this case, because we picked up the second book, aka index 1, we're going to compare it against our first book, index 0. Hence, we're going to do I minus 1. And this comparison is going to see if it's taller or shorter. Taller, stay in place. Shorter, swap, and insert to the correct place. So our iterator j is going to be what we're going to be using for our condition in our while loop. So why are we using a while loop and not a for loop in this case, right? So I tell my students this because they don't use while loops all that often, but I always try and tell them and remind them that while loops are really good when you have a undetermined number of iterations that you may have to do. For loops are great for, well, starting at a spot and going till a certain condition finishes. Like it is a determined number of iterations we're going to have to do. But we don't know how many times we're going to have to make that comparison of a shorter book in that sorted region. We might have to insert it 6, 7, 8, 9, 15, 100 times until it finds its correct position. So we don't know how many times we're going to have to compare and insert our newest unsorted book into our sorted region. So that type of operation is really useful for a while loop because while loops are good at that. Some unknown number of iterations that have to occur, and we're going to provide a condition for when they stop, and it's going to just keep going until that happens. Whereas for loops are good for a determined number of iterations, right? Starting at index 1, loop through the length of the array, moving by one element at a time, and that's it. This while loop could go 1 time or 50 times. We don't know. We're going to provide the condition for it to do so, and that's really about it. So we have to continue for as long as j is not negative, right? Because once j is negative, we don't have any other books to compare to because we're outside of the bounds of our array. The lowest this number can get is 0 because that is our very first book in the array. So we're going to say so long as j is greater than or equal to 0, meaning it is not negative. How we're going to think about that. So long as j is not negative, there's no negative index positions to look at in the array. So logically, we would have to stop by the time j gets to that point. Yeah, and as long as the item at index j is bigger than our current comparison, we're going to continue this thing as well, right? Because, well, if it's bigger, then we don't have to continue. So we're going to say, also, if array element, so if the element at position j, so in this first iteration is index 0, aka our first book, in the array, we're going to compare it to our current, which is 1. So we're looking at the first 2 books together. So rj currently represents the first book we assumed was assorted in the very first iteration of this whole thing. And current will be the second book on the shelf, meaning if it is taller, we are done. If it is shorter, we have to swap. So we're going to say, as long as this is bigger than current, right? This is how long the while loop is going to run. So continue as long as j is not negative, right? Meaning we haven't reached the beginning of the array. And as long as the item at index j is larger than the current item, because we get to insert and swap it, right? So if that's the case and it needs to be inserted on over, what we're going to do is say, right, get that value and assign it as the new rj for our swap. And then move j down by 1, so we've moved it, and then we continue on that process right there. And that's all we have to do. Yeah. And then once the correct spot is found, right, rj will no longer, the element at position j will no longer be bigger than current. So once we finally had found a book on the left-hand side that is not bigger than our current book, meaning it's smaller, then we have theoretically found the correct position of our element, which means that we then insert it there and call it a day, which is done by this code here. Assign the current value to the current position of j plus 1 after our loop is done moving through, right? So that means that the correct spot is found, once again, that the element at rj is no longer larger than current, or when j is negative. We then place the current item into that spot. So we get that spot and place the current item in there, which is our insert. And the outer loop will move to the next point of the next iteration of the array. So then it will then go to 2 and then do the whole same process over again. Just simply compare and grow our sorted region up over time, right? So yeah, and just like before, once that whole process is done, we should be able to take a look at our array, return it for testing purposes, and for, no, not await. Stop it. Stop the autocompletes. Yeah, we should be able to return our array and log it to take a look at it, and that is all we got. So let's see if this works really quickly here out of curiosity. And I'll try and cover the explanation once again. Yeah, there you go. 11, 12, 22, 25, 34, 64, 90. That is indeed a sorted array of values, right? Like I had said, the code for this is not that bad whatsoever. It's just understanding what we're trying to do, which I might actually leave this code as is for now. I'm not going to change anything. I mean, before I re-explain it, let's cover some of the other aspects of this algorithm, like its big O and some comparisons and pros and cons. Then we're going to look at the visualized, again, from Timo Bingmann on YouTube, the visualized version of this algorithm. Discuss it, then come back and take a look at the code and talk about it once again. So yeah, let's do that this time. So in terms of the big O notation, the complexity of this particular algorithm, this one varies unlike the rest in complexity. So in terms of space, though, we can say a space of, you guessed it, 1. Mostly because, as you can see, we don't create any other growing variable other than this, like the simple assignments, which again don't require any additional memory. There's no like growing secondary array. It's an in-place sorting algorithm just like the rest, so you don't see some other like returned result we're generating here. So it's an in-place, which means all these are pretty much just going to be a space complexity of 1, just a linear line, right? Now, the difference here compared to the other ones is we actually have some potential differences in the time complexity. So, best case time complexity, unlike the rest, can actually be a possible of big O of n, which we haven't gotten on the other two. Why is this the case? Because if our input array is already sorted, right, the algorithm will only need to pass through the array once to check that everything is in order. Whereas in the other ones, it would have to do multiple comparisons over and over and over again, the bubble and selection sort, meaning we'd always have to run all of our double for loops. Whereas if this one never actually has to run its internal while loop, it only runs through everything one time, and in best case, we get a big O of n. But again, that's best case. Worst case. Worst case will be a n squared, right? That exponential line that we've looked at in our picture here. Let's go ahead and grab it wherever it went. Big O diagram, yeah. Don't forget our n squared is just that line that generates up. Big O of n is just that linear diagonal line right there. Big O of 1 is just a straight line across because it's a 1, right? That's all it is. So yeah, that's the worst case scenario for our algorithm, right? Because if the input array is like sorted in reverse order, the algorithm will then have to go through and shift each element n number of times, giving us that quadratic, that's what I was looking for, quadratic running time right there. And then average for this one is also an n squared at average, right? Average case time complexity. If it's in a completely random order, each insertion is on average halfway through the sorted list, so it needs to shift about half the elements depending on how randomized it is. So worst case, n squared. Average case, probably n squared as well. Absolute best case is a big O of n. So why is this one a little bit different than the rest, right? That is because this one has the ability to adapt depending on our input array being partially sorted or not, right? Because of that, because of that adaptive nature, which is one of the reasons why this is cool, so I'm kind of double dipping into my other sections, performance will improve considering how sorted our input array is, right? That's why this has this best case time of O of n, if the minimal number of times this while loop has to run. It's not going to always be this quadratic scenario. So that's why this algorithm is cool to learn. So yeah, in terms of pros and cons, simple implementation, right? The fact that we can write this code out fairly simply once we understand what it's doing is a good pro for this particular algorithm. It is efficient, just like the other two, for small lists, right? Small lists, these are good choices as far as sorting algorithms goes. And this one's even better if you know you might have a nearly sorted input list already, right? It is very efficient when dealing with small lists or lists that are already partially sorted. And those cases, we get closer and closer to our best possible time of an n. Remember that linear diagonal line. So that's what's so cool about it. It's in place for a sorting algorithm, which means it doesn't generate any extra overhead beyond the original list. So there's no growing secondary list or array or things like that. It's also a stable one, like the other ones I've talked about. Insertion sort is a stable algorithm, meaning that the equal elements retain the relative order. I don't think I covered that in some of my other videos. So as a quick idea of what I mean by stability, it's the ability for algorithms to preserve relative ordering of equal elements in the sorted output. Meaning, let's take a look at this example here as a code example real quick. Let's say we have an input that has a list of students. Student 1 gets a score of 90. Copy paste. We're going to say student 2 gets a score of 80. So we're just looking at like an input list of some students. And as you can see, like the students' names are kind of like the keys in a JavaScript object, if you will, whereas their scores is what we want to sort by. So like these are how we're going to identify the students, and these are their scores that we're going to be sorting here. So in stable sorting, here's what we would get. Our output, let's say input, stable output. And if we're like, hey, I want to write an algorithm that sorts it from descending order from highest to lowest. And you're thinking, Luke, that's already our input right here. And you're correct. A stable output would produce the same thing. Student 1, 90. Student 2, 80. Student 3, 80. Student 4, 70. If you had an unstable sorting algorithm output, you can have the potentially following happen. You would have the same output, except you may get the point where student 3, a score of 80, is swapped with student 2, who also has a score of 80. If these two student keys are reversed, we are dealing with what we would deem a unstable sorting algorithm, meaning it has the potential to, when values are equal, to swap the position of their keys, right? Again, that's what I mean by maintaining a relative order by preserving keys and their values when they are equal, right? So that's what I mean by stability here. So stable means, in all things being equal, the keys will also be sorted and remaining in place if values are equal on the sort, whereas unstable sorting algorithms may produce different key positions, which would mean they are unstable. So that's the big benefit of the insertion sort. It is a stable sorting algorithm, which also makes it kind of cool compared to the others we've discussed here. In terms of cons, right? Again, not great for large lists. We'll talk more about the other ones like merge, quicksort, and heap sort are better algorithms for large data sets. So these first three ones are something you could memorize for quick answers in an interview, going, what's good for like a small data set? What's good for a small data set that's already slightly sorted? Boom, you got some answers right off the bat right away until we cover the next one. Cons, number of swaps. If these books have a really bad order, or like I said, if they're reversed, swapping elements might be an expensive operation. In this case, they're just integers, not that big a deal, but if they're like large data structures of some kind, swapping their positions may be very costly and overhead in their nature, so that could be really bad if you have a high number of swaps. And like in that I mentioned reverse order array, in worst case it's quadratic n squared big O. And it's also really dependent on the initial order of elements, right? So the efficiency of this algorithm is pretty dependent on the initial order in your input, right? It is a very good advantage for nearly sorted lists, but a big disadvantage on completely random or inversely sorted lists. So that's a very important thing to remember about insertion sort. It can really, really bite the dust if you have a reverse ordered sorted sorted input list you're trying to deal with, insertion is not good for that. So yeah, in terms of like I said, why it's cool, it's adaptive, meaning the performance will improve if our input is already partially sorted. I think that's pretty cool to know about this one. And it's the normal stuff as well. Thinking about performance is a good test to learn here. This is a good foundational one for bigger picture topics and things like that. And as always, just passing your freaking interview is a good reason to know some of the high points on this particular algorithm, right? So in terms of comparison, remember bubble algorithm would continually iterate through the list, and it would swap adjacent elements if they were in the wrong order until the list is sorted, right? So that would bubble a big element to the top, and it'll keep comparing and bubbling the big elements to the top, which is a quadratic n squared big O. It's considered the least efficient of the three algorithms on large lists. Selection sort was dividing the input into a sorted and unsorted region. It kept on selecting the smallest or largest element from the unsorted region and moves it to the sorted region. Remember, the selection sort also had a worst case time complexity of n squared. And then insertion is similar to them in that it divides into a sorted and unsorted region, just like our selection sort did. However, it will repeatedly take the first unsorted element and inserts it into the correct position in the sorted part of the list. So for lists that are, again, repeating myself, already sorted, it gets better and better in terms of its performance, right? So that's just a quick reminder of what we mean by those values being for the comparison of bubble select, and now our third one we're adding to our repertoire of insert. My goodness, trying to keep my head straight and say all these algorithm names correctly is going bonkers here. But let's go ahead and toggle over to the YouTube video. Again, thanks for Timo Bingmann for visualizing these a decade ago and being so relevant today. This is our bookshelf we are looking at here, and because we have kind of like a sorted beginning here, it'll be slow to pick up, but once it gets the sorted region built out, we get going here. So right now we've made the assumption that this red book is our first sorted part of our sorted region. The rest of the white ones are all the unsorted region right now. The green one is our for loop starting at position 1. That's just our current, and we're going to compare the current to our sorted region. And we're going to say, hey, is the one on the right shorter or taller? Because it's shorter, we swap them, and then that whole process will basically ask that same question over and over and over again. So starting this out, we can see that all those big ones are getting sorted, or all the smaller ones are getting sorted to the left, and our sorted region is growing. It's simply taking that smallest one, going, you're smaller, you're smaller, you're smaller, you're smaller, you're smaller, you're smaller, and then boom, does the swap, for loop iterates, goes to the next one. So whenever you see that red bar jump to the far hand side, that is our for loop iterating. And this inner part, this comparison right here, is that while loop that we had written together. So when you see those two reds moving inwards in our sorted region, that is that while loop running that comparison. So long as j is not less than 0, right, it will continue comparing. And as long as our current element, which was our rj code in the while loop exit condition, or terminating condition, whatever it's called, that rj, so long as it's bigger than current, we then iterate downwards, right? So that's because that element we're looking at, so long as the one before it is bigger or not is bigger, we continue on, right? But when it's not bigger, we do the swap and we're done. So yeah, as you can see, it's picking up speed now that our sorted region is looking good. And again, I'm not going to play the sound on here because I haven't configured my OBS to like capture the desktop audio. I haven't tested to see what this sounds like, but it sounds, I'm trying to talk over it, so it sounds ridiculous. I'm trying to talk over this sound it does here. If anyone's like clicked on the links in my description to actually watch these videos, the sound, they're pretty funny. My wife hates them and drives her crazy because I'm playing like this audio effect. So yeah, we can see that sorted region getting bigger and faster. Remember, if it's shorter, we swap and insert it to the next position and then run the same comparison. So the red bars moving in are our while loop, and this leading green bar would be our for loop here. And as you can see, we just keep on finding the smallest book and inserting it to the correct position in the current sorted region until we wind up with our completely sorted array. Yeah, so let's go back to VS Code. There we go. I don't think I've changed anything in the file save-wise. Yeah, so once again, that was that leading part of the sorted region, that green bar that over time grew and grew in the sorted region every time that for loop ticked over. We saw that sometimes that while loop was running that comparison swap a number of times over and over and over again until it finally inserted the book into the correct part of our currently sorted region. It's like, okay, well, this is now the smallest book we've found so far. It will go at the beginning, right? But those number of comparisons would drop dramatically if that input list was already partially sorted, as you saw from that visualization. So this part, I think, was here the trickiest to understand. This part's easy, because remember, that's just making sure we're not out of elements to compare against, being the beginning of the array. And this was our the element we're looking at j compared to our current I, right? So that's all we're looking at right there. And then once that book needed to get swapped over and we're done comparing and we're saying, oh, this is now bigger than the one on our left-hand side, then we are inserted there and we are good to go. And that's all that happens. Yeah. So, I mean, like, as always, y'all, I would like to say, I hope y'all enjoyed this video. If you found it helpful in your journey to becoming a better developer with me as well, because it's been really fun for me to dive into these algorithms and, again, try and understand them well enough to explain them on a video can be difficult. Y'all know out there that you can probably get something but not get it well enough to try and explain to somebody else. I try and find myself explaining these algorithms and how they work to my wife on our evening walks we go on, because it helps me understand it better and can teach me where there might be a downfall in how I teach these on video to you guys and gals. So if you enjoyed it, please give us a thumbs up and consider subscribing to our channel for more videos like this. I would also love to hear y'all's thoughts on these, and any kind of constructive and positive comments are always welcome here. So let's keep the discussion going and help each other in our coding journeys, y'all. So thanks again for tuning in, and I'll see y'all in the next sorting video.